Here we're going to have lesson 3. This is mesh motion with moveLungMesh. And last time we constructed an anatomical mesh with NetBHex mesh. Should look something like this if you cut it open in the slice function in ParaView. And now we're going to figure out how to have this structure move in a custom way to solve some biology fun problem. Here we're going to talk about breathing. So our test case is going to be this iguana mesh, and you can see it's pulsating in and out, and we're going to try to make our mesh do this. We need basically first to build a motion library, and that's going to be in the src pulsating point patch vector field directory, and we're going to have a .c file which has our equations and a .h file with our name for this motion library we're going to build, and that name also has to get reflected in the make then files directory. The commands we're going to use to build this thing are wclean and wmakelibso. So how are we going to do this? If you look at the motion we have down here, it's basically a sine wave. It goes in and out over time. So your motion is going to look like this. And the first equation that generates that motion is this sine wave, and that's found in pulsating point patch vector field .c. So local amplitude, which we'll define later, multiplied by the normal vector, so all these points are going to move in the direction of their normal, multiplied by a sine wave. The sine is going to be of 2 pi, this is open foam for 2 pi, multiplied by some frequency, and that's under control of the user in /point displacement. So if you change that frequency, you're going to change the period of the sine wave here, multiplied by the time. So every time, so this is a graph here, so this is time, and this is the amplitude on the sine wave. Okay. Importantly, the motion is going to vary by patch name. So in this lung down here, the type of motion is different between the ventral chamber, the dorsal chamber, and the trachea. And the way we're going to accomplish that is with this local amplitude term of this sine wave. So in another part of pulsating point patch vector field .c, we're going to find this local amplitude for every point on a patch. It'll be different for every patch. So that'll be done with this equation. So it says calculate local point displacement amplitude for all points on the patch, and the local amplitude is going to be equal to some amplitude, which is a a constant, and that'll be in 0 point displacement. So whatever motion you generate, if you were to say make the amplitude higher or lower in one patch, you can change that in 0 point displacement. These patch names have to be the same patch names that you have in your constant polymesh boundary directory. And the easiest way to make the motion customizable is to parameterize the mesh domain into X, Y, and Z and code your motion pattern in terms of that. So here in this iguana video, you can see the middle part of the lung moves more than the tips. So if Z was going from back to front, we would actually it would look like this. Local amplitude would be kind of a parabola. But for now, we're just going to learn how to code it where it would vary from Z max to Z min. So either the front or the back of the lung would move maximally, and the other end would not move at all, because that's an easy thing to code. So I've shown you how to code that up here, where essentially Z max, the local amplitude is equal to amplitude multiplied by the maximum Z point minus whatever point you're at, divided by Z max minus Z min. So if you were at Z max, you'd have 1 minus 1, say, divided by 1. So you have 0. And if you were at Z minimum, you'd have 1 minus 0 divided by 1. So 1 divided by 1. So here you're going to vary where Z max is 0, the local amplitude at Z max is 1, and the local amplitude at Z min is 1. I said it backwards. The local amplitude at Z max is 0, and the local amplitude at Z min is 1. So let's learn how to do this. So if we go into our open foam directory, we've got a src file. We'll go in there, and we'll also have pulsating point by vector field. So we got to do, and there's another pulsating point by vector field. First thing to do is change the name of your pulsating point patch vector field library. Because every time you make one of these, I'm going to give it a separate name for each simulation. So I'm going to change the H file, and when I go down, eventually I'm going to see type name equals pulsating tutorial 2. Whatever you change this to, let's call it pulsating tutorial 3, is going to be what it's called in OpenFOAM. Right, and quit that. And we also have to change in the make directory, in this files case. Then files, let's call that lib pulsating directory tutorial 3. Now, these names are important in two places in your simulation. One, in the system control dictionary file. So the control dictionary will tell OpenFOAM which libraries to source. We need to source the one that we are going to use. So libpulsating tutorial 3.so. And in the 0 point displacement directory, for every boundary patch we need to have that's going to move, we need to tell it what to do or which one to use. So we're going to just use the ventral chamber here. So the type of motion has to be pulsating tutorial 3. That's what we want. If we don't want the thing to move, we can just change the type to fixed value and the value to uniform 0. So that's what I'm going to do. I'm waiting for the other chamber here, this dorsal chamber. Comment all this stuff out. Type fixed value, uniform, 3 zeros, which is the one. Yeah. I forgot a semicolon. Okay, so here for the ventral chamber, the type of amplitude, pulsating tutorial 3, we're going to change the type in a second. Amplitude is that scalar term that will multiply the sine wave value up or down. Frequency changes the period of the sine wave. So let's right quit. Okay, so let's edit our library to make it customized. So we'll go in, I'm done yet. Change directory pulsating. Okay, here we're going to edit the C file. So at the top of the C file is going to be a whole bunch of stuff, and eventually, which you can ignore, and eventually you're going to get to something that says look up patch name, okay? And then if the patch name is X, do all this stuff. If it's not, go to the next thing. So here, if whatever we put in this area is going to be the motion library for the ventral chamber. If we wanted to have motion for another chamber, we could change it down here. So for else, so if not, if it's something called right long, then apply all this stuff. And if the chamber, or the patch rather, the boundary patch doesn't match any of the names in this file, it won't get any motion. So let's edit the one for ventral chamber. So the first thing you'll see is origin and radii from problematic locations to prevent displacement. And to show you what I mean by this, we'll look in ParaView. So here's our ventral chamber model. And we can have that expanding and contracting, but it's touching the trachea model. So if this expands and contracts, it's going to displace away from this trachea and make a break in the mesh. We don't want there to be any motion here. So what I'm going to do is create essentially a sphere around that spot where there is no motion. And the way to do that is at the bottom here, where I have that local displacement amplitude, we're going to have local displacement of what we want, and then multiply it by this function. So take the maximum of this or 0 and multiply it, and then the minimum of this or 1. And so what this minimum function will do is return a number somewhere between 1 and 0. And this max function will return a number somewhere between 1 and 0. And this will make sense if you think about it after a few minutes, but what I'm doing here is essentially saying that here's the origin of this point. That's the origin of the sphere. We're going to have a small and a large radius around it. So anything that's this far within this distance of this vector, then we're going to make the motion a 0. Anything that's more than this distance away from that thing is going to be a motion of 1 down there. So we're not going to affect our other code that we're going to write later, other equation. Anything in between these two values is going to vary from 0 to 1. So in geometric speak, that means that get rid of this slide for a second. That between, say, here and here, there'll be no motion, but then once you get to here, there'll be normal motion. In between there, we'll ramp the motion up, and that will prevent the trachea from displacing against the ventral chamber. So you need to find the location of that origin point to plug in there, and I think the easiest way to do it is use a slice function in pair view and get that slice in the right coordinates in terms of z, y, and x, and then just get these numbers here and put it into the equation there. I've pretty much done that already. Okay, so there's the vector origin, and to calculate the radius of each point on the patch, so the distance from every point on this patch from that spot, we're just going to use the distance formula. So here point I is like the point in question, and we're going to use the distance formula from the origin of that 1 there. And if I wanted to use multiple conflicting regions, I could comment out number 2, number 3 here, and then this code that went along with it. Okay, so going back to our PowerPoint, what we want to do is have the motion vary from Zmin to Zmax. So we need to tell the code to identify the minimum and maximum Z points for the whole patch. That's what we're doing here. And then take every point on that patch, this is this part of the code, subtract it from Zmax, divided it by Zmin divided by Zmax, and then multiply that thing. So this is going to this radius thing. And that'll give us a local amplitude for every point on that mesh. Okay? And then if you are curious, that sine wave function we talked about before is at the bottom. These are other patches, and I can use them if I need to. I can also leave them alone. Okay, so if you try to call this motion library pulsating tutorial 3 in a patch, and then you don't list that patch up here, you're going to get this error where this bound recognition is not meant for the patch, blank patch name, and then it's going to give you a fatal error. So you need that. Okay, and then you've done some funny business over here, but essentially now point displacement is equal to local amplitude. Local amplitude was calculated for every point way above up there. Now we're going to multiply that by the vector normal to that point to get the direction, and then the sine wave of 2 pi multiplied by frequency, which is defined in 0 point displacement, and the time. So for every time we're going to get that. And then there's some smoothing at the bottom that you can kind of change if you want. So escape :WQ to write that. Now we need to do a W clean, W make libso to write our library. And it should come out at the end. Lib pulsating tutorial 3.so is up to date. That lib pulsating tutorial 3.so is what we called in system control dict. Okay. So The last thing we need to do is build this thing called moveLungMesh, and that's actually the solver that will deform the mesh in one direction or another. We need a moveLungMesh directory in SRC. There's a C and H. You don't have to change anything about these. You just have to do that same wclean and wmake. Let's do that now. moveLungMesh. Go into that directory, wclean. And actually, we just need a wmake, no libso. If it's not a library, it's actually an executable, I think. And do it again just to make sure you get that. moveLungMesh is up to date. Okay, we're almost done. We need to do one more thing. We need to do this thing called toposet dictionary. And what we're going to do is essentially create a box in which everything is called lung or whatever you want. But so that moveLungMesh knows what to calculate the volume of. So here we're studying breathing. We want to know the volume of the lung after it's deformed at every time step. So you need to know what is the lung. So the lung is going to be anything inside this box. We're defined by xmin to xmax, ymin to ymax, zmin to zmax. And that toposet directory is going to be found inside system, toposet dict, and this will be a long file with everything commented out at the bottom. We're going to make a cell set called lung, anything inside this box. So going back into your para view, you can say, all right, I want the lung to be from Z max, that's about 0 here, Z max, to Z min about negative 0.04. Okay, I got 07 there. Or sorry, wait a minute, I did it wrong. Negative 0.15, negative 0.15. For y, we do the same thing. So the maximum y needs to be about 0.15. Okay, you get the picture. Fill in the x and y. It's wclean. And now we have the dictionary for that. We have to actually make the cell set. To go per our case directory, write topo set. Okay, so we read toposet dict. We created a cell set lung with everything inside these boxes. Now we have a cell set. We need to actually make it a zone. So sets to zones. No flip map. Overriding the contents of existing cell zone 0 with that of cell set lung. And this is going to be in the constant polymesh directory. You can actually see it there if you're curious. And there should be something called cell zones. You can look at it. And, well, I should have looked at it from the top. Lung. And this is all the cells that are in there. Cool. Let's see if this worked. If we go up to BiOS CFD tutorial, we can write, just do a moveLungMesh. See if we get any errors. Command not found. Okay. Sometimes this happens where you have to build things twice. Let's try this again. Command not found. I'm gonna do source open foam again, and actually I'm just gonna exit. I think it's something to do with this fastx container. Sometimes this happens. Do it again. Okay, I should have the source open foam. Okay. Don't know why that is. Okay. So first error. Cannot find the file dynamic mesh dict at line 0. And constant. So it turns out we need that. That's cool. We didn't have that. Let's see if it's in the system. No, I need to borrow that. Well, my other simulations, I'll put it in the tutorial here. Let's copy all this stuff. So, okay. Yeah. Okay, fix that error. Try it again. Okay, here it calculated the lung volume. Okay, and we have a okay, and just skipping up ahead a little bit, we can create a Slurm file to do this in parallel. Pretty much exactly like we did for Snappy Hex Mesh. So we can look at our Slurm file, and all I've done here is set the work directory, all the normal stuff, and then when I'm running the job, I want to decompose par, MPI run whatever number of processors, moveLungMesh instead of Snappy Hex Mesh. The log file is going to be whatever you want to call it. I said moveLungMesh. The important part is here, we're sourcing OpenFOAM. In the earlier part of the tutorial, we sourced OpenFOAM 2.3 before we built our pulsating libraries. And here I'm sourcing OpenFOAM 2.4 to do moveLungMesh. You have to have built or compiled the pulsating point patch vector field library and the moveLungMesh in the same version of OpenFOAM that you're going to use. So just a heads up. And I've done this, and I've reconstructed one time step here so we can look at what the output is. Pull up Parafoam. Right, that's the problem. It doesn't exist in that version of OpenFOAM. You might not have this problem on your setup. Okay. Parafoam. I'm doing this just to show you what you should see. So after you've run this moveLungMesh for a time step or two, and how to check your work. What's cool is we can go to our latest time step, and we can color our mesh by point displacement. We have to first load that in here as a Lagrange point field. And then we can load point displacement. Okay. And if we look at our color map, point displacement goes from 0 at blue up to red, some higher value, and there's a clear, this patch, this patch, this patch, this patch are unaffected, and the ventral chamber is coded where Z maximum is 0 and Z minimum is a higher number. So this is how you check your work to make sure you've coded your library correctly. And now go ahead and make it go. Change your, you're going to iterate your sine wave until you get function, until you get the sine wave you want. You can change the parameters in 0 point displacement. So let me show you that. And you can change the magnitude of motion also in 0 point displacement. And you're going to have to play with that and the delta t to get the right motion, to give you the right tidal volume without breaking your mesh. So in that point displacement directory for ventral chamber, if I increase the amplitude, I'm going to move the lung walls more. If I change the frequency, I'm going to change the shape of the sine wave. And I can change my delta t in System Control Dictionary. So good luck playing with your motion and getting the motion you want. And then in the next tutorial, we'll talk about how to compute flow from that motion.